Good afternoon, everybody. Welcome back to the afternoon session of the fourth day of our symposium. So I request Professor Josna Kumargiri of Indian Institute of Sciences to chair this session. Josna.
Yeah, thanks, Kajari. So let us get started with the afternoon session. So we have 4 talks in this afternoon, and first talk is by Professor Mauro Donica. So before we start, let me introduce the speaker to you. So Mauro Donica is a senior scientist at ETH Zurich, Switzerland, and he's presently working on the CMS experiment at LHC. He got his PhD from University of Geneva in 2006 and his master from University of Milan, Italy. He worked mainly at Hadron Colliders, CDF at Tavatron, and Atlas and CMS at LHC. And his research interests focus on detector development, basically silicon trackers and electromagnetic calorimetry, and also collider physics. He's presently working in Higgs physics and searching for physics beyond the standard model through precision measurement of the Higgs boson. So today he's going to talk about Higgs STXS measurement. So Mauro, the stage is basically, I'll zoom over to you and you can share the screen and get started.
Okay, can you see the slides?
Yes, we can see the slides.
Thank you, Josna. Okay, good afternoon, everybody. So today I'm going to be talking about STXS simplified template cross-section and fiducial cross-sections measurements. First of all, I have to put in a bit of a disclaimer. That is that the most relevant and updated results from Atlas and CMS about these 2 topics, STXS and fiducial cross-sections, have already been presented in previous talk this week, actually in quite some details. So when I saw that, I said, okay, job done. I don't have to give a talk anymore. And so I decided to instead change a bit the tack of this talk. And instead of focusing on the plots themselves, I'd like to focus on how the results are obtained. So basically, take a step back and try to see how the ideas behind the measurements were developed. And again, given that basically all plots have already been shown, I have the privilege of only picking the ones that are relevant as examples to convey the message that I want to give. So like often happens with birthdays, it's a good time to look back and see what we've done so far, what we did well, what we didn't do so well, and where to improve next. So 10 years ago, we were at this point, we saw this bump. We very quickly actually moved on to measure its quantum numbers. And by all means, this really looks like a standard model Higgs boson. Now, the point is that we will never be able to confirm that this is the standard model Higgs. The only thing we can do is to prove that it is not the Higgs boson. And the way to do this is, apart from finding physics beyond the standard model, that would be an obvious way to show that the standard model is not the ultimate theory. But what we can do is already disprove that is the standard model Higgs by doing precision measurements and accompany this with accurate theoretical precision, accurate theoretical predictions. So before going on into how we set up the measurements, maybe it's interesting to look at maybe a trivial question, that is, why particle masses are so interested in high energy fields. So if you think about the typical LHC collider, it's a multi-TeV center of mass energy. And the masses we're talking about are order of 100 GeV, okay? So essentially for everything we do in experimental particle physics, it should be totally irrelevant. So the energy is so much bigger than the mass. Instead, even at the LHC, the mass of the particle, it's not just an irrelevant correction, but it shows itself with qualitatively different effects. Like if you have a massless spin-1 photon, then it only shows the 2 polarization up and down, while if you have a massive spin-1, then you also have your longitudinal polarization. So you have 3 degrees of freedom instead of 2. And as people like to say, 2 is not equal to 3. So it's actually qualitatively different what you see. And the Higgs mechanism essentially is the easiest way to fix the bookkeeping of all the spins of the spinning massive particles. Now, there is a catch that is the Higgs boson itself is not spinning. It's actually, it doesn't have charge, it doesn't have spin, it basically has only mass. And so who's giving the mass to the Higgs? And the point is that it's the Higgs field itself through self-interactions. And this vertex here, it's essentially the simplest vertex you can write down. And it's the only vertex we've seen where you don't have any change of quantum numbers at the vertex. And this is something that is completely new and would like to study this in all sorts of details. Now, here I'm quoting an excerpt from an interview that Nima Arkani-Ahmed gave at the CERN Courier titled "In for the Long Haul." I'd like to read these two sentences just to set a bit the framework of what I'm talking about. So Nima says, so if the biggest excitement for you is a cross-section plot with a huge bump in it, possibly with the tickets to Stockholm attached, then after the discovery of the Higgs, it makes perfect sense to take your ball and go home, since we can make no guarantee whatsoever. Now, here it's, of course, pointing in two directions. One is, okay, the LHC is still a discovery machine, so maybe this bump will come up. This we still don't know. And this, we can make no guarantees of this source whatsoever, refers back to the no-lose theorem that we had with the Higgs, that is either the Higgs is there or something else has to play its role and we will discover it. So it continues saying, we're in for the business. We're in this business for the long haul of decades and centuries, and if you don't have the stomach for it, you better do something else with your life, which is a quite interesting comment. Now, then it attaches a message to the experimentalists, and this is where we start my talk, essentially. While we continue to scratch our heads as theorists, the most important part forward for experimentalists is completely clear. Measure the hell out of these crazy phenomena. And this is exactly what we will try to do next, and I will quickly summarize in this talk. So there's a lot to learn by studying this boson. First of all, we can ask if this is really the standard model Higgs, if this is the only source of electroweak symmetry breaking we have, if this particle is not an elementary but is a composite particle, what is the shape of the potential of the Higgs? Does the Higgs violate CP? Or does the Higgs violate the flavor? And so if you look at these questions from the point of view of precision measurements, simplified template cross-section or fiducials, you see that many of these questions can be addressed by doing this kind of measurements. Now, the point is that the more we know, the more we want to know, in a sense. So after the discovery, we started immediately characterizing the Higgs and making a very model-dependent, taking a very model-dependent approach. We were assuming that the signal comes from only one particle. Remember, at that point, we weren't even sure about that. Maybe there were two very close particles with a very small split in mass, and we had to make such an assumption. The standard model, the boson we see is really the standard model 0 plus standard model Higgs, and also in terms of production and decays behaves a standard model. And we use the narrow width approximation, so essentially we decouple production from decay. The first things we were doing were to compute signal strength modifier, these famous mu's that were appearing in all plots, that are simply the ratio of the production times branching ratio that you're measuring divided by the expectation of the standard model. Namely, mu equal to 1 would go to, we measure a standard model Higgs, mu going to 0, there's no signal. Any other value of mu would be a particle, but not the standard model 1. That's a very coarse way of looking at the characteristics of this particle. And the next step in the direction of having better understanding, better tools to characterize the particle was to introduce these kappa modifiers, the coupling modifiers. These are now modifiers pushed down at the amplitude level instead of just at the cross-section level. And this has an advantage that with these kappas, you can be sensitive to interference effects. And in particular, take just an example. For instance, here, you can, by playing with the kappas, you can play with interference between these two diagrams, the top and the W diagrams in the Higgs to gamma-gamma decay. And by measuring the gamma-gamma decay, you can infer the patterns of interference here. It's a very powerful tool. Then, armed with these tools, we went on and tried to hunt for BSM effects, and the hunt is still ongoing. So BSM, beyond standard model, affects what we see in different ways. It can affect in the total number of signal events, but also in their differential shapes. So places where you can look for BSM are, for instance, in gluon fusion production of the Higgs. That is a top loop in the standard model production. And so here in the loop, you can have all sorts of new strongly interacting particles contributed to it. Or you can look at very boosted gluon fusions on the tail of the PT of the Higgs, where the standard model at this point for you conceptually becomes your background. And so the standard model Higgs PT dies out, and if you have a deviation, that could be a signal for BSM. Or you can look in VH production. Here you have an intrinsic boost coming from the recoiling on the V boson, and here you can, for instance, check for momentum-dependent couplings. The VVH has no momentum dependence in standard model. Or the VBF, which is super rich because you can test both the Higgs and the gauge sectors, the Lorentz structure of the VVH coupling, and the CP of the Higgs. The TTH for the top Yukawa. Of course, this is a super challenging analysis. Or directly in the decays, the XBV is the test of the standard model, is where you have basically Glashow, Salama, and Weinberg put together the unification with the gauge bosons of the electroweak theory, and also the couplings with the fermions, which are described through Yukawa interactions that, again, are the simplest you can imagine, but again, maybe it's not what nature decided to put in place. In order to test all this, what we want to do is to invent new measurements to probe the largest possible phase space and with the highest precision. As you see from this slide, the phase space is really huge, and we want to do the best job we can in order to characterize it. So let's take as a starting point of this journey for these slides, the signal strength modifier. So here, the typical analysis goes, you collect your data with the trigger, you apply some selection cuts in order to suppress backgrounds, then you categorize your events to enhance the sensitivity. In these categories, you put in some signal extraction procedure that could be mass fit in the X gamma gamma or DNN fits in the XBD, some complicated way to constrain backgrounds from control regions, and so on and so forth. And then in the end, you do a combined fit of all these categories and you extract the signal. So if you look at just one category, I hope you can see the mouse. The number of events in a category that is what we measure, can be written in this way. So essentially, it's the usual luminosity times cross sections times branching ratio, but then you have the effect of the efficiencies and the acceptance of your detector. You sum up all these contributions for every production and decay mechanism. And this is essentially what you would expect from the standard model. And in front of it, you put this mu, which is the modifier that you want to fit. And of course, here you also have the contribution from backgrounds. So you measure the green quantities, the red ones are coming from standard model, and what you fit is this blue mu. And now you can just extract the mu and be happy with that. Or you can also rewrite mu in terms of some theory parameterization, be it EFTs or whatever else. And then by fitting mu, you can put constraints on this parameterization. Now, if you play this game, you can extract the maximum information from your data, but of course you have also to pay the price of maximum model dependence. So here essentially is you plug it in the standard model and you see if how your signal in terms only of this mu will differ from it. We can do better measurements. And so in order to design better measurements, we want to have some criteria just to guide the definition of better, what's best, what's better, what's worse. So of course it should allow us to extract the maximum information from the data. The information we get should be as model independent as possible, and this model independency will be the guiding theme of many of the slides. And it should be presented in a way that allows for future or different reinterpretation of the data. Very practically, from an experimentalist point of view, including new or different theoretical prediction, it's a pain in the neck because you essentially have to run a lot of stuff. So if you can decouple the measurements from the interpretation, this will come as a great bonus. So essentially what we want to have is to shift the theory dependence from the measurements itself to the interpretation. So make a measurement which is essentially model independent, and then the interpretation comes at a later stage and you can do whatever you want there. Typical thing is you have a better standard model modeling, the N, fourth and fifth LO description of your process, that should only affect interpretation. You don't have to rerun the analysis for that. Now, out of the many solutions that were on the table, I'm focusing on two. One is the simplified template cross-section that I will call STXS for short. And the other one is the fiducial cross-sections, both total cross-sections and differential in observable. These two solutions at least partially fulfill all the requirements listed in this slide. Let's start with the STXS. As the Higgs boson, we say, was born the 4th of July 2012, we said that the STXS were born in Les Houches in 2015. Of course, it's an exaggeration. The idea was there was before. If you want to have a document that spells out the basics of the measurements, this is the link to go to. So the goal here is to maximize the sensitivity of the measurement, but minimizing at the same time the theory dependence, using the smallest number of partitions of the phase space that we are analyzing. And these partitions of the phase space is what we call the STXS bins. So what we do is we measure cross-sections instead of signal strength modifier. The measurement is done in simplified fiducial volumes. This is what we call bins. We allow for the use of multivariate analysis or machine learning tools to extract the signal. And then in the end, we combine all decay channels. So essentially, we don't look at the decay side of the process. We only look at the production. The central concept are these STXS bins that are chosen to minimize the theory uncertainty, maximize the sensitivity of the measurements, isolate possible VSM effects, like putting bins at IPT in order to isolate possible contributions. But at the same time, we want to minimize this number of bins without loss of experimental sensitivity. And then we start with a small number of bins and when increase it, the number of bins with time if we have more statistics, or we can merge them together in case of low statistics channels. In the end, we also want to have something that is easy to combine because the bins are set up in a way that are mutually exclusive in kinematics. We all agree on the definition, so Atlas and CMS, and within them, all the production and decay, all the decay channels all use the same binning. And once we want to publish these results, we publish the full set of measurements in the bins plus the covariance matrices. So this can be used later on for interpretation for theorists. So let's see a bit more in details what all these words means. So essentially what we do is we start from what we wrote before for the signal strength modifier. And the STXS are essentially a simple extension to this. So we move from given a ADK, we move from the production bins into STXS bins. For each of them, we have obviously the same expression, but now we multiply the mu in the bin times the standard model cross section. So if you want this number here in the end, this product, it's a cross section, and it acts as the standard model template in the STX bin. This is where the name template comes from. The kinematic properties still are defined in terms of the full phase space. So this is the acceptance here, but the STXS bins are defined in order to minimize the theory uncertainties in each of them. So let's see a bit more what it means, how to reduce the dependence on theory uncertainties. So there are several aspects related to this. One is we want to avoid large variation of acceptance in one truth bin. And so if you have a situation like that, you prefer to typically split the bins in two, such that within each bin, you have a pretty flat acceptance. Remember, if you don't have a flat acceptance in a bin, if you have any trend, then that trend automatically implies a model dependence within that bin. And so if you make it flat, you essentially kill the dependence. You can use MVAs, but it is delicate. The point is that one has to choose carefully the MVA that is using. The selection on MVA should be mapped in some specific region of the phase space, and ideally close to what you would obtain with simple cuts to avoid weird migrations from one bin, STXS bin, to another. And another thing you can do to reduce model dependence is separate out regions of the phase space where you would expect to see BSM. And typically these are the tails of the distributions at IPT, for instance, and other corners of the phase space. Then once you have the measured cross-section, you unfold them to the STX bins. And of course, here is every time you use an unfolding procedure, you will introduce a model dependence that comes from the way you build up the response matrix, if you want, of your unfolding. And another thing we typically try to do in STXS is to reduce model dependence is to keep the definition of the final state particles as simple as possible. Essentially, the goal would be to have the Higgs boson as a final state particle itself. And this is what really allows to have a simple combination. So you don't have to take care about the final state. You only look at the production. So this was the first step in STXS. Basically, it's this production mechanism splitting that was using run one. And you see here in this plot, now this plot is with the full statistics of run two in X gamma gamma, how it looks like. So basically you write out for each production mode your mu value. And so here you have the gluon fusion, VBF, VH, TTH, BBH, and TH. Worth noticing, BBH and TTH typically we don't have sensitivity yet to address them. And VBF and VH are split in a rather peculiar way. VH, we only mean the associated production with a vector boson that decays leptonically. This is because when the V boson decays hadronically, at higher order, this distinction is a bit ambiguous. So essentially, you can't really separate out, for instance, QQ bar to an hadronic decay V plus X from the VBF. And same thing goes for gluon fusion and gluon to ZH. So these are essentially the same diagrams. And so we merge them together in this. So we talk about QQH. From stage 0, you can go to the next granularity, which was called the stage 1. And essentially, you see the gluon fusion, for instance, was now split into jets. And then within the single jets, you were looking at different PT bins. So you try to make it more and more granular to extract more and more information. And similarly, you were doing the same thing for VBF and VH. The present state, we went from 0 to 1 to 1.1, and now we are at 1.2. I'm skipping over 1.1. It's irrelevant for the following. 1.2 is now quite a detailed description in terms of bins. So for instance, here for gluon fusion, you're separating out what we call high PT from low PT with a cut around 200 GV. And the high PT binning is essentially there to test for possible BSM. Then you have in the low PT is split by number of jets and PT with the idea of starting essentially QCD radiation. And this one in particular here is 2 jets with a high MJJ, the invariant mass of the 2 jets in the event. And this is interesting because it's essentially a possible source of background for the VBF category, where you have these 2 high eta jets as a signature of your VBF that could be mimicked by a gluon fusion with characteristics in these bins. And then, of course, we do the same for the RS, for VH, for QQH, and now in stage 1.2, also the TTH is split in PT bins, higher and higher granularities. So this is a pretty fantastic plot that shows all this binning. Now, this is done only for X in gamma gamma at CMS. And you see, we're now spanning about 3 orders of magnitude in cross-section. And for the first time here, and this is really the impressive part, we are able to do a differential measurements in PT of the X in gamma gamma, which is pretty astonishing. Now I show you a couple of plots for the various measurements we've done in XWW, just to show the main characteristics. Again, all the details, unfortunately, have already been shown before. You can refer to those slides or ask me at the end details if you want. I also add a couple of slides with the detailed bibliography, so that if you want to check the various ones, various measurements, you can check them there. XWW is the workhorse for many of our measurements. It's a coupling to vector boson, has a pretty large cross section. And here you see how it's now binned into, sorry, there's a question from outside? No, okay, someone has opened the mic. Then X to 4 leptons, this is the so-called golden channel because of the mass resolution that is achieved in our detectors. And here you see instead the problem of not enough statistics. And so some of the bins have been merged together. So this is the typical thing you resort to do when we don't have enough statistics for this classification. Another example is the X to tau tau. Now here you take advantage of a couple of things. But first of all, that it's a coupling to a lepton. And so it's per se extremely interesting from the physics point of view. But it's also true that it has a relatively large branching ratio, so you can explore corners of the phase space that would be otherwise precluded from other channels simply because the cross-section is too small. And BB is a case where you can really push to a very high boost, so PT above 400 GeV. At that point, the two B jets from the Higgs are so boosted that they essentially merge, and so you have an analysis where that looks at this merge jet. So you have essentially reconstruct one jet, and then through techniques like soft drop, you can figure out that you have two Bs and get the and feed the soft drop mass to extract the signal. STXS has the advantage that they're designed with the idea of also having combination in mind. And so here is a great plot from Atlas that shows a combined measurement of several channels. Here you have gamma gamma, ZZ, WW, BB, tau tau, and also Z gamma, all together with the stage 1.2 binning of the STXS. And the reason why I'm showing this, apart from the fact that it's an amazing plot, it's because there are some messages to take from this, especially on the theory dependence. So a measurement like this will have a smaller theory dependence than the actual total cross-section, simply because now the efficiency time acceptance are computed in each of the bins. And so in this case, you have essentially you breaking it down in smaller chunks where the effects are, where the acceptance, if you want, it's flatter. And so here you reduce the theory dependence. And then the assumption about the kinematics within a given STX region still leads to some model dependence. And so again, as we were saying a couple of slides ago, the goal for the future will be to take these bins and then increase the granularity, and so add more and more bins to reduce that one. With this combination, you can also do, but not only with this combination in particular, but following this line of thought, you can start interpreting the measurements with whatever model you want. And one of the interpretations that are proposed is in terms of EFT. So effective field theory. In this case, the standard model is seen as a low energy effective field theory of some higher energy complete theory. It's called the UV completion. The standard model is now completed with dimension 6 operators, and out of the about 2,500 operators you can put in that contains the standard model fields and respect the symmetries of standard model, you can isolate only a very small subset by plugging in some assumption. And this is what Sally was describing in her talk earlier this week. And with a smaller number of operators, you can try to take your data and use them to constrain these operators. In this case, they went down to 13 EFT operators written in the Warsaw basis, which is kind of agreed upon basis to be used by everybody. These 13 EFT operators impact the Higgs interaction, so our data can put some constraint on them. If you try to do brute force a fit on the operators, the fit will not converge simply because the data don't have enough information to constrain all of them. And so what they've done is to play a trick. It's a kind of principal components analysis, if you want. So they take the 13 dimension basis and they produce a rotation that effectively what does it groups together operators that have similar effects on data and tries to get rid of a flat direction. Flat direction is essentially a direction in this 13-dimensional phase space where the data have no information. So bluntly put it, they can't bend the likelihood, they can't have meaning there. And so with this kind of data sets coming from the STXS, you can have actually the first constraints on some of this combination of operators. And so more granular, less theory dependence, easy to combine, and easy to then interpret. The other solution that is put on the table instead of the STXS, which is complementary, if you want, to the STXS, is the so-called fiducial cross-sections. Here, the goal is to really push the measurements to the maximal model independence. Here, there is no date of birth of the fiducial cross-section measurement that's been there forever. You can see a description of this applied to the Higgs in the yellow report 4 at that link, but essentially these were there from lab, before lab. I guess that the concept is it comes natural with the idea of cross-section, so it's always been there. And so what makes a fiducial cross-section different from a simple inclusive cross-section is that in the inclusive cross-section, you extrapolate to the full phase space, what we call the 4 pi. And by doing this extrapolation, you also cover regions that are not measured by your analysis, or they're actually removed by your analysis. You typically do this extrapolation because theory predictions are computed in 4 pi, in full phase space. So if you want, in a situation without a detector that puts any acceptance, that makes the comparison possible. But because you're doing the extrapolation, you have to plug in some assumption of what you use to extrapolate, and that brings in a model dependence. Instead, the fiducial cross-section try to go in the opposite direction. You define a fiducial phase space, which is essentially dictated by the detector acceptance, where you measure the cross-section. And you try to avoid as much as possible these large extrapolations. So you account for deficiency and migrations in your measurements, and you have, and we'll show you in the next slide, possible migration inside and outside the acceptance from resolution effects and beam-to-beam migrations. The measurements are then unfolded to particle level, and in the end, what you have is a factorization of the experimental from the theoretical uncertainty. Using the fiducial cross-section measurement, now you can compare with the theoretical prediction that can be BSM, of course, but it can also be different accuracy modeling of standard model. You can compare the measurements with this prediction by correcting the cross-section by the new acceptance. So in this way, you will see that it becomes very easy once you have the fiducial to plug in the new acceptance from your model and then compare with theory. Maximal reusability of the measurements. So these are the two goals: maximal theory independence and reinterpretability of results. So this is a sketch to explain a bit what I was trying to say in previous slides. So here I'm in a fake two-dimensional phase space. In reality, you can imagine it in as many dimensions as you want. You can do fiducial in PT, NJets, rapidity of the Higgs boson, PT of the leading jets, whatever. Okay, here I'm just taking two observables. And the point is that you have reconstructed bins that are defined on the quantities we measure with our detectors. And these reconstructed bins do not line up perfectly with the particle level bins that we're defining. Take the example of PT. If I have 0, 50, 100 GeV reconstructed, these cuts do not map one-to-one to the fiducial 0, 50, 100 GeV, simply because the measurements have resolution effects, and so you can have migrations. So here in this sketch, these light blue are the bins at the reconstruction level, the RICO bins. In dark blue, you have the beam migrations. And then outside here, you have the fiducial region in which you would like to do the measurements, the fiducial region that you try to put as close as possible to the reconstructed fiducial region. And you have events that are produced in the fiducial region, but they don't enter your bins, and these are it's effectively the efficiency of your measurements. And then you have other events that gets reconstructed outside the fiducial region, but they get reconstructed in one of the bins. And this is the typical example where you put a PT cut. The event is actually generated below the PT cut, but because of resolution effects on the PT, they can migrate and pass into your fiducial phase space. All these effects of migrations are we try to reduce them by choosing carefully the phase space. So trying to mimic as much as possible, to match as much as possible the reconstructed phase space with the fiducial defined at particle level. So to limit the model dependence, we try to have the fiducial region, RICO, and at particle level as close as possible. And typical, the choice of this fiducial region has to take these points into account. First of all, the detector acceptance. You have a finite volume of the detector that covers up to a given region eta, and then you might have cracks in phi, and so on and so forth. You have selection at trigger level that have a kind of a low resolution on line cuts. And then you have the analysis selection cuts, which are typically higher resolution and put a bit tighter than the trigger level to avoid any possible turn on. Any selection at reconstruction level has to be mimicked at particle level. So one point is try to keep it as simple as possible. Try to avoid NVAs. If you cannot avoid NVAs to do the signal extraction, so you can't keep it simple, try at least to make sure that the phase space that you extract behaves somehow in some easy to model way. Think about replacing it with cut paste. So have something that can be made by cut paste. If you take the example of the X gamma gamma, for instance, what do you define as a photon in our detector? It's an object which has an electromagnetic cluster and low isolation energy around it. To have the best possible separation between photons and jets faking photons, we set up a BDT, a multivariate approach to this problem that allows to have the best separation between photons and fakes. But effectively, in the end, we cannot transfer this BDT into a physical region of the phase space on the photons. And so what we do is we try to, when we have to define the fiducial region, we try to replace this by essentially applying cuts on isolations that try to get the same similar performance to what you get with BDT. And of course, because of the not perfect matching, then you will have these effects of migrations. You also have out of the fiducial phase space contribution. This is stuff that comes from outside that is reconstructed outside your fiducial phase space that is reconstructed in your detector. And this is treated as a background. And then an important point is that the fiducial phase space is different for each final state. Take the example of the gamma gamma and the ZZ. The gamma gamma will have a fiducial phase space based on PT and eta of the photons. In the ZZ, you will have a fiducial phase space based on momentum of the electrons and muons in the final state of the Z. How do you match the two? There is no way to match the two. You can't compare apples and oranges here. And so here, this will become a critical point when we have to combine measurements. So again, how does a fiducial cross-section look like? Back to our formula. So the number of events here binned at RECO level is the usual sum over all production processes of luminosity times cross-section. In this cross-section, we also include the acceptance. And then you have this matrix here that is, in a sense, the bridge between the truth world and the reconstructed world. It's called the response matrix, and it contains all the efficiencies and resolution effects. So essentially, the response matrix gives you the probability for an event produced in a true bin J to be reconstructed in a RECO bin I, okay? And so, for instance, if you sum over all i's, so you take what's the probability to have an event produced in a given bin at true level to be reconstructed anywhere, this gives you back the efficiency in that bin, okay? Now, the formula is essentially the same as before. The important point is the fiducial cross-sections include the acceptance, and as before, these fiducial cross-sections now you can rewrite in terms of theory parameterizations. Take the example of the EFT we've seen before, and now by fitting these fiducial cross-sections to data, you can put constraints on the theory parameters. These response metrics depend strongly on the resolution of your measurements. If you have a value like a PT for a diphoton that is measured with high accuracy, the probability that you generate a photon in a given bin and you construct in the same bin at Rico level, it's very high. And so the migrations on the borders are going to be very small. And this is what you see in a matrix like this, where you see on the x-axis the generator level bins, and on the y-axis the reconstructed one. So this one is essentially a diagonal matrix. You can also have cases where you have large off-diagonal elements coming from beam migration. In these cases, and jets. In worst cases are, for instance, when you reconstruct in the WW the PT of the Higgs, because of the missing momentum coming from the neutrinos, you have a big smearing on that, and so you have large out of diagonal elements. And this will, we'll see, will need some regularization when we do unfold. So the role of the acceptance in this technique is the following. In the inclusive cross-section measurements, we correct for the acceptance. And so by correcting for the acceptance, we automatically introduce a model dependence coming from the theory that you use to compute this acceptance. The acceptance is computed at particle level, the generator level, effectively, where you essentially count the number of events that enter in your acceptance divided by the total number of events that you produce. In the fiducial cross-section, the acceptance is in the fiducial cross-section definition. We don't correct for the acceptance, and so we don't have a model dependence for it. This means that it makes the measurements reusable in the sense that whoever wants to compare a new model with the data can reintroduce the acceptance computed with this new model. Typical theories that come up with a given model can compute the acceptance with its model, multiply times this fiducial cross-section, and get out a way to compare it with the predictions. Despite all this, we still have some residual model dependence. One comes from the unfolding, as usual. The unfolding, again, is moving from reconstruction space to the truth space, particle level. The model dependence comes from the fact that this response matrix here, which is essentially the integral of the phase space of the distribution of the signal times efficiency, can depend on the parameters of the model. In particular, the signal distribution can depend on the parameter of the model and so affect the matrix. How can you reduce it? Well, one way is you make smaller bin. So you try to make the model flat in each of the bins that you're using. And the other one is trying to have the efficiency as flat as possible. Again, whenever you have any shape within the bin, you split the bin and you try to make it flat. Another residual model dependence comes in the signal shape, and it's unavoidable. Suppose you're reconstructing an invariant mass for your X candidate. The invariant mass will depend on the kinematics. Take again the example of the diphoton. The higher the PT of the photons, the higher the resolution of your detector, of your calorimeter. And so the narrower is the bump. But your physics model can affect the kinematics of your signal. So you can change parameters of your model that affects the kinematics. If the parameters change the kinematics, will also change the width of the resolution of your invariant mass. And so this will have an effect, will be a residual of theory dependence on the signal. And of course, the last one is on the, yeah.
Yeah, 10 minutes left.
Yeah, I'm getting there. Thank you.
Thanks.
And then, of course, on the background, you can have effects of of your theory parameters on the background itself. And so when you subtract the background, you have to take into account that you might have effects there. Final point of comparison, STXS are not fiducial differential cross-sections. They are different things. In the fiducial cross-section, we optimize for maximal theory independence. The acceptance correction are minimized as much as possible. The measurements are unfolding to a phase space, which is as close as possible to the fiducial volume. And we're almost completely insensitive to the production mode. This is good for model independence in a way, but it's also true that then when we go to a case where we have a production mechanism, a scheme of production mechanisms like in the standard model, gluon fusion, VH, BBF, and so on, it means that all plots we will see will be dominated by gluon fusion. Essentially, all the interpretation we'll do are effectively only sensitive to gluon fusion parameterizations. On the STXS side, instead, we allow the use of MVA at the cost of having larger acceptance corrections. This is always something that has to be treated carefully. We are inclusive in XTKs, and this simplifies a lot the combination side. And we are completely agnostic on the details of the production modes because we are using these kinematic fields. How to link observable to physics? We want to measure the cross-section as a function of different observables, and depending on the observables we measure, we can attack different physics points. Like if you study PT and jets and so on, you are sensitive to QCD radiation. You can be sensitive to protons PDF, to in VVF production, you can describe the vertex by measuring these quantities here, which are essentially quantities based on the system of the Higgs and the two jets. And in particular, the delta phi JJ will allow you to test the CP structure in VBF production, cos theta star, the spin, and so on and so forth. So every observable helps in constraining one or more of these physics items. Some results out of this. So first of all, fiducial cross-section, even before going to the differential side, are used to produce total cross-sections. So here you see two examples of fiducial cross-section measured at different center of mass energies of the LHC. This is the X4 leptons for CMS and in Atlas. This is a new plot that shows gamma gamma and ZZ together with the combined value. And I'm coming back on how to combine this in a second. This is the evolution that we had in the PT measurements of the Higgs in gamma gamma from the early round one results where we were extending only up to 200. Now we go much higher. And you see that from the initial 2016 to the full run 2, we added an awful lot more bins. And again, anytime I show any of these plots, I don't repeat all the time. There is no significant disagreement with standard model because it's the same story everywhere. We're now capable of producing about 25 differential cross sections in gamma gamma 1D, and we're also producing 2D cross sections like this one. Where we measure the PT as a function of a number of jets, 0, 1, and 2. So we can go more and more differential. The trouble there is, of course, the statistics we have. The larger number of dimensions, the larger the statistics you will need. You can also do other tricks, like you can enrich some regions of the phase space by applying some cuts. Again, to preserve model independence, you don't want to have an MVA that selects, I don't know, VVF region, but you can select a phase space in the fiducial region that is close to the region covered by the VBF production mechanisms, for instance, in this bin, or you can look for PT miss, where you will have a neutrino in final states or number of B jets close top or number of leptons and so on and so forth, okay? This is another example that is particularly tricky is the WW. Because of the neutrino in the final state, the PT resolution is very poor. And so this is a specific case where the unfolding procedure requires a regularization term. And then you can also combine measurements. And here I'm showing you a plot of combination between ZZ and gamma gamma from Atlas. And the point here is that how do you combine the two? Because the fiducial phase space tested by the gamma gamma and ZZ are defined on variables that are different. One is PT of the photons, the other one is PT of the leptons, for instance. And so the way to produce these black dots here that are the combination is you take the measurement, you expand them to 4 pi, you combine them at 4 pi. Okay, so what you see here, it's the combination that comes after the extrapolation. When you do the extrapolation, then your super model independent fiducial cross section buys the model dependence of this extrapolation. And this is something we have some ideas on how to bypass, and I'll come back to this in a couple of slides. Now, this is essentially the same idea. It's an older example. We're combining now X gamma gamma, ZZ, and BB in PT and in other quantities. But the point here is that I wanted to show you is how to use this combined spectra in order to get some interpretation. So we do the same game, we extrapolate for pi, we multiply the likelihoods of the different measurements, and then what we do is we take our theory prediction in terms of whatever coupling modifications we have or EFT coefficients, we parameterize the cross section in terms of coupling, and then we fit to data. And here are two models. One is from Massimiliano showing how the PT spectrum changes as a function of KT, KG, and KB, kappa T, kappa G, and kappa B, sorry. And so here you see various numerical values of these parameters shows you different PT because you have a dependence on PT, you can fit it on data and constrain these parameters. And here is the same, but now instead of looking at the high PT region where you have the largest sensitivity, now you look at the low PT region where you're sensitive more to kappa B and kappa C. And this is a plot from Ulia et al. When you do interpretation, you can use differential information, but also the inclusive cross-section are very sensitive to couplings. For instance, here it shows you how the branching ratio changes as a function of kappa B. And here, as soon as you move a tiny bit around the kappa B, because of the large cross-section, the large branching ratio to the B quarks, you see that immediately basically saturates completely the width of the Higgs. So it becomes only BB. And so this kind of inclusive cross-section have already just on the inclusive side a lot of discriminating power. You can do these kind of plots where you can fit kappa T to CG. CG is another way of looking at an effective coupling to the gluons. And you can put in different assumption. One, assuming there is no VSN contribution, so more standard model-like, and you see you have a very good constraint, or you can remove that and profile also the branching ratio, and then here you see that the constraints and also the degeneracies will change in your plot. And here is another example where you fit kappa B and kappa C, and you see what happens if you assume no VSN contribution, so you use the branching ratios from standard model, or which effectively means you use both shape and normalization, and you get very constraining profiles, or you use the shape only, removing information from the normalization, essentially fitting also the branching ratio of gamma gamma and 4L, and you see that you have a much less discriminating profile. The same thing was done for Atlas. Now back to this plot, this new plot for the combination, and you see here exactly the same plot, but now produced with the full run-to statistics. This is particularly interesting because now you can set up a competition between measuring the effects of the couplings of the Higgs to the charm through measurements of differentials and the direct search for the Higgs to CC. Now, in the last couple of minutes, I want to show you other ways of using these measurements. One is now to fit n fiducial differential cross-section in one shot. And so here now we're fitting, Atlas is producing this plot where it fits PT, NJets, MJJ, delta phi JJ, and PT of the leading jet, all together to EFT coefficients. And now the point here, they can do this in X gamma gamma because they can work out what is the correlation between these measurements, essentially working out what is the covariance matrix here, by resampling the data, producing the correlation matrix that you see in this side here. With the gamma gamma, you can do it because you have a large background, and so you can resample your cross section. So you resample your data and you recompute the cross section to get to the correlations because you have a large background. This, for instance, cannot be done with XSec, where the background is very limited and the resampling will fail. And this is a very interesting way of reusing these measurements. Final one, there's another way of using this cross-section measurements that, again, like with the coupling to the C that enters the competition with XSec direct measurements, you can also go in competition against the direct search for Higgs production. And this is what happens if you look at higher order, even the single Higgs production has a dependence on the trilinear coupling, exemplified in some of these diagrams here. And if you look at the effect of changing this kappa 3 in theory language is our lambda. If you change in lambda to these values, you can see, especially for TTH, you have quite substantial effects on the PT of the Higgs. And now Atlas produced this plot where they compare the double X production to the single X production, and then the combination of the two. And you see that the two, the constraint from the single X and the double X are actually not too far away. So next, it's run 3. Run 3 in terms of center of mass energy, we go up to 13.6, which in terms of production cross-section for the X, it's essentially irrelevant. But we're going to add a lot of luminosity. So we're going to add another about 300 more inverse femtobar. Anything new with this larger statistics? Well, of course, we redo everything we did before with larger statistics as usual. But maybe we can do also something new. That is, in this STXS, for instance, we're preparing now the stage 1.3 within the LSCX working group. And this may include, of course, a finer beating, a larger coverage at IPT, but also most probably some bins that are sensitive to CP violation. For example, something in delta phi JJ for the VBF. And in fiducial cross-section, this comes back to the theory interpretation. I'm closing. I'm really done. When we have to combine measurements, we are forced to go into this 4 pi extrapolation. But in reality, what we could do is we can also take all the measurements in their own phase space and then multiply the likelihoods together and fit directly the combined likelihood. And this is something we've never done before, but it's very promising. So in summary, we've gone a long, long way from the discovery of the Higgs boson to all the measurements, procedural measurements we've done so far. The measurement techniques and interpretation frameworks are becoming more and more refined. We're only entering run 3, and the path to the iLumi, it's very long. It will last for another about 2 more decades, which are 2 more reasons to give these kind of talks and to celebrate. But from the experimental side, this also means that we're in for the long goals on the detector operations, calibrations, computing, and this is really a huge collective effort that has to be sustained for a long, long time. So here we see all this super cool multi-dimensional differential distributions that are sitting on the work of many, many people on the detector side. And of course, so far, this looks like a lot like the standard model Higgs, but maybe it's not. And it's really up to us to disprove it. Thanks a lot.
Yeah, thanks, Mauro, for the nice talk. So anyone has questions? Like Kajari raised her hand, and then Ram. Kajari, can you unmute and speak?
Thank you, Mauro. This is really quite extensive talk and state of the art of the analysis regarding STXS and Fiducial. I did not understand quite a few things. Could you go to slide number 17?
17. Yeah.
So, so when you said that use of MVA is delicate and to reduce this dependency on theory uncertainties, I understand MVA is quite convoluted, so we cannot readily map, one can say. So how do we do away with it?
Yeah, so,
yeah, tell me.
So here is one of the main things between Fiducial and STXS. So the use of MVAs is the thing that blurs a bit the boundaries between the two. Yeah. In the STXS, we do use them. In Fiducial, we try to avoid them. The reason for this is the following. Instead of looking at this problem from the STXS point of view, look at it from the Fiducial side. So for instance, you're familiar now with the gamma-gamma analysis through the BB gamma-gamma, for instance. In the standard analysis of the gamma-gamma, we use a classifier to distinguish QCD diphotons from Higgs diphoton based on a BDT. Now, this one, if you just use it as it is, it will try to fish out the events that look more like Higgs, independent of where they sit in the phase space. So in the case of a higher score of this BDT, you might have something that is maybe high PT and maybe a bit outer in eta, together with maybe something lower PT, but is more central. They're high in the score, but they're mixed up in phase space. And this can create some troubles. Now, if what we try to do is to be careful with this, so we avoid using this, for instance, in the fiducial measurements for gamma-gamma. There we use a simple classification based on the resolution on mass that has nothing to do with complicated. It's easy to map in phase space. And in the fiducial cross-section, sorry, in the STXS, we always try to have an eye on these possible effects of the MVA on the actual regions. So we have to try to avoid that the MVA mess up completely the model dependence. That's the idea, basically.
That is really good. But then what happens is that our samples will be not very signal dominated. So, or rather, if we are strict with our selections, that means we have to restrict ourselves to only few final states, which were large yield.
Yeah. So, and now if you take your argument and you push it to the extreme, you can go back to what we were doing at the very beginning. Now, something like the strength modifier, it's the most the most model-dependent thing you can do, but it's also the most aggressive. You can extract the maximum information out of this. And it's really the balance between anytime you put in model independence, you're by definition less constraining. The more you push on the model dependence, the more constrained you are. But again, that's the balance we were trying to figure out with these two methods. It's a very good point.
What about slide 28?
28.
Oh, yes.
Yeah.
So can you please again tell from the beginning, because I'm yet to really appreciate how exactly we are doing this EFT analysis. Sorry.
Okay. No worries. I was very quick on this. So here the point is the starting point. It's again what Sally showed in great details a couple of days ago. So no theories today is believed to be the final theory. They're all effective field theories of some higher energy theory. So it's low energy approximation of some UV completion. In the case of the standard model, we can complete this theory with the higher order operators. So we set a say an energy scale below which we expect no effects from BSM, and then once you have defined this this cutoff, we can produce an expansion on these lambdas in terms of dimension 5, 6, 7, 8, and so on operators.
Okay.
Each of these will be renormalizable, and so it's a complete theory. Now, dimension 5 and 7, they violate baryon numbers and so on. So we focus on dimension 6 and 8. 8, we have essentially no sensitivity, so we expanded with dimension 6. If you just use that, you have about 2,499, I believe, operators.
No, okay, let me put it more pointed way. So my point is that we have many observables.
Yeah.
We try to express them in terms of a set of EFT coefficient parameters or operators, whatever you call it.
Yeah.
So what tells us that where exactly we should stop in that expansion, say for example?
The expansion in, sorry, say it again.
In the, when we write the Lagrangian, the EFT, so where do we stop to express these observables? So we stop at dimension 8, that's all.
Yeah, so the point is, that's related to the cutoff. So every time you go higher in dimension, the effect of those operators will be suppressed by this cutoff to the end. So the effects are going to be smaller and smaller. We decide to cut at dimension 6 because effectively we have no sensitivity to dimension 8, modulo some details, but that's the idea. So that's where we cut.
Yeah, but what I am confused about is that which are the observables we will take that will sort of show visible, or you can say interpretable.
Right. So this is the typical exercise that we're all doing in these days. That is, you have a bunch of operators. So in this case, they picked up this 13. And then you want to see which observable is more sensitive to which operator. And so typically what we do is we go a bit brute force in these cases. So for instance, here, what you could do is you take, in this example, you take SMEFSIM. So essentially you have a plugin to MATLAB. You generate events with MATLAB by changing the parameters of the EFT. And then you look at all the observables that you have, and you see which observable gets the biggest hit by changing the parameters. Okay. And here you have to take some approximation. So typically what you do is you change one parameter at a time, and you see which of these gives you.
Okay, maybe I was missing this. Okay.
And if you look in any of our combination, you will see tons of these plots lying around.
Okay. Okay, I think I should stop and let others. I have quite a few more questions, but I will contact you later. Yeah.
Sure, you're welcome.
Thank you. It was very nice. Yeah.
Yeah, Ram is the next person. Ram, you can.
Hi, Laura, can you hear me?
Yeah, I am.
Yeah, my question is on slide number 34.
1 second, 3, 4. Yeah.
No, sorry, 33, the one before that, where you said that like you have to avoid MVAs in the fiducial cross section one.
This one.
Slide. Yeah, avoid when possible use MVA. Now, given that like most of the Higgs analysis have moved to MVAs, not just DBT, actually multi-class neural networks. Let's say TTH is one example of that. So these like MVAs are not only like optimized for, let's say, standard model Higgs versus standard model backgrounds, but basically designed to distinguish one process from another, say TTH from TH, and so on and so forth. And because during training we have all assumed standard model 125 GV Higgs kinematics and everything, and at the end of the day, every Higgs analysis will give you is a data card in which you have the data observed and each and every process the shape systematics and their respective yields, again as histograms, whose meaning also has been optimized separately, depending on what analysis they are doing. So how will you all use these to basically use this information to reinterpret, say, in light of some new BSM scenario which were not designed before, or we are not in this case?
Yeah, so we're back to Kajari's point. Again, there are not all channels are equal. Some channels are easier, Some channels are harder. So if you compare gamma gamma towards, I don't know, TTHBB, essentially in TTHBB, there is no way you can extract a signal without using any MBA, any sorts of DNN or something like this, BDTs or whatever you need. If you go in that direction, you are assuming a given model dependence. Why? Because you want to extract a signal that is essentially an X with associated top production. There are ways, so you're buying in some model dependence. There's no way out. The more complex is the final state, the more you do it. There are some ways to avoid this, that is trying to make these trainings a bit softer in a sense. So you can try to put it in the training data sets, not exactly the standard model characteristics, but modifications of the kinematics coming from, I don't know, your EFT-inspired coefficients that are not as aggressive on the details of the model. And in this case, your sensitivity will go down because you pay for that, of course, but at least you gain some more flexibility. That will be an issue. So that will be an issue for the maximal model independence of these measurements. Something in between is what they're doing with the STXS. So essentially, you will try to buy in some model dependence coming from that, but you're focusing on, you essentially go to TTH and then you bin in this large bins of PT, and there you try at least to compensate with the large bins to have, say, less dependence on the details of the production. But yeah, I'm totally with you. These kind of things will have an impact on the differential.
Yeah, thanks.
Yeah, so Arnab, if you have a quick question, can you ask? Like, we are running really late.
Yeah, may I ask? Okay, so first of all, thank you for the nice talk. I had a question on slide 19 or maybe 27, whatever we choose. So we see that sometimes, yes, this one also, and also similar side in X2WW. So we see sometimes we apply cuts on variables like, let's say if we take the VH process, we could apply cut on the PT of the vector boson in the final state. So what if we apply cut on the, let's say, mass of the vector boson and Higgs combined, something like the invariant mass of the vector boson and Higgs, not PT? I mean, my question is how these variables are decided.
So that's a very good point. And same thing goes with TTH. What is a top, for instance, is the same thing. So the point here is you want to avoid to plug in direct information on objects that are not precisely what you're trying to measure in theory. So for instance, in the top case, or VH or whatever, in the top case, what you're really sensitive to from the theory side, it's the top that then will dictate W and V. And so, for instance, in those cases, you're looking at quantities on the top itself because they allow you to reduce the theory uncertainties on its kinematics. All the variables you see here, including the binnings and all these mergeable bins and so on and so forth, are all designed in order to have, from the theory side, cuts that allows you to have small uncertainties. So essentially, anytime you cut on PT, you're going to have problems with resummation and so on. And people are trying to go from, this is a big difference with respect to the differentials. They're trying to look at the cuts, not from the experimentalist point of view, but try from the theorist point of view to see if I cut here, what kind of effect I have on the uncertainties. From the experimentalist point of view, we throw as many bins as we can compared with the sensitivity you can get. From their side, all these variables are chosen on that. And of course, this is one way of doing this. It's the typical one proposed by Frank Tachman. But of course, one could come up also with other biddings that you totally.
Okay. Okay. Thank you.
Yeah, thanks a lot, Mauro. So probably we'll switch to the next talk.